It's time to master the art of ionic nomenclature. Writing ionic formulas and naming ionic compounds should be something that you've done in the past, but it needs our attention now. It's something that you're going to do all year long, and so we really do have to master this skill. We should be able to write ionic formulas forwards, backwards, upside down in our sleep. So I'm hoping that this all comes back to you. There is a little trend with valence electrons that we should recall from last year. I'm hoping that you remember everybody in the first group has one valence electron. Everybody in the second group has two valence electrons. And later on, we'll look more specifically at atomic structure and s orbitals, p orbitals. You might remember that group 1 alkali metals will all have an electron configuration that has one electron in the outermost s orbital. That's its valence electron. Group 2, the alkaline earth metals, will all have an electron configuration that has two electrons in the outermost s orbital. We'll skip the transition metals. When you fill those d orbitals, they don't follow trends real great when it comes to valence electrons. They don't follow a lot of trends, period. So we'll skip them for now, and we'll deal with them in a few minutes. When we jump across to the boron family, everybody has 3 valence electrons. The carbon family should all have 4. Nitrogen family is 5. Oxygen family is 6. The halogens all have 7. And for the most part, the noble gases have 8 valence electrons. As we go across this p block from boron over to neon, we've got the s orbital that has 2 valence electrons, and now we start adding electrons to the outermost p orbitals until we get across to the noble gases where they have 8 valence electrons, 2 s electrons, and 6 p electrons. Now obviously helium is an exception. Helium only has 2 valence electrons. He's just filling the first energy level, but I'll keep that 8 up on there. Hopefully that doesn't bother you too much. We can use this trend to predict charge. We're going for 8 valence electrons in most cases. So if you have 1 valence electron and you want 8, it's probably easier to lose 1 rather than gain 7. If I lose 1 electron, I have an extra proton. Everybody in group 1 has a charge of +1. If you have 2 valence electrons, it's easier to lose 2 than gain 6. All of the alkaline earth metals have a charge of +2. Now, transition metals are going to have kind of wishy-washy charges, and sometimes they have more than one possible charge, which is, again, why we'll kind of skip them and move over to the boron family. For the most part, the boron family will have a charge of +3. It's easier to lose 3 electrons rather than gain 5. But that brings us to the carbon family. We've got 4 electrons, we want 8. Gain 4, lose 4. You can go either way. So for now, I'm going to write plus or minus 4. But what we'll find later on is that often the carbon family will bond covalently. Instead of transferring the electrons, often will share. Now, that doesn't mean that we can't transfer. So I'll leave that plus or minus 4 up there. And that'll apply to most elements in that group. It's kind of the turning point. When we get over to the nitrogen family, now we have 5 valence. So it's probably easier to gain 3 than lose 5. By gaining 3 electrons, our charge is -3. If we already have 6, we'll gain 2. All the oxygen family elements should have a charge of -2. The halogens will all be -1, and we're going to say 0 for the noble gases. That's something that I would probably write on a periodic table. If you use a periodic table in your planner or in the AP packet, if you have your favorite periodic table, I would write that down. The more you look at it, the more it becomes ingrained in your mind, and you'll never, ever forget it. But we need to be able to find the charge on any ion, and that's going to be one thing that I will definitely use. That gives me most elements on the periodic table, just not the transition metals, which we'll deal with. I also need to be able to find those charges quickly so that I can write formulas. So the idea of writing a formula, an ionic formula, is that we've transferred electrons and we should form a neutral compound. So we want to look at the charges on the individual ions. And I mean, the more you write formulas, you'll get good at it. And sadly, you'll have a lot of these charges memorized. Maybe that's impressive. I don't know, check with your friends. They might think you're really cool if you have ion charges memorized. But that's always my first step. I need to acknowledge the charge on magnesium ions and iodine ions. Magnesium is in group 2, +2. Iodine, halogen. They should be -2. -1, hello. And again, if you can do this in your head, great. And hopefully, eventually, you can do this in your head. But for now, you may find yourself wanting to write the charges on paper. If you don't write them down, you at least need to acknowledge the periodic table and look at the charges. Now we need to make this neutral by adding subscripts. A +2 charge means that magnesium would like to lose 2 electrons. Iodine would only like to gain 1. Well, we have to somehow transfer both of the electrons from magnesium. That means we need to make this neutral overall. This is some complicated math. But what if I multiply this times 2? Then I have a +2 and a -2. If I need to multiply the charge by 2, then I need 2 atoms in my formula. Mg. I2, magnesium iodide. I like that. Now again, you don't have to show work for these. I'm hoping that eventually you can do this in your head, but you definitely need to acknowledge the charge. If somebody's got a formula written wrong, 90% of the time, it's because they don't have the charges right. Aluminum nitride. Aluminum's charge is +3. Nitride comes from nitrogen, -3. Aluminum would like to lose 3 electrons, and nitrogen would like to take 3. It's perfect. It's neutral as is. ALN. It looks kind of funny, but it's done. It's neutral. Calcium phosphide. Calcium's charge is +2. Phosphorus, -3. It's in the same group as nitrogen. We need to make this neutral. Calcium would like to give away 2 electrons, but phosphorus needs 3. This is pretty common to have 2s and 3s. Our common multiples probably 6. And again, if you can do this in your head, which I'm hoping you can, you don't have to show work. You don't have to write the charges on paper. But you need to acknowledge the charge. You have to look at a periodic table unless you're going to memorize them all. Those multipliers then become my subscripts. It means that I need 3 atoms of calcium and 2 atoms of phosphorus. That should give me a complete transfer of 6 electrons, leaving me with a neutral formula. Not only should I be able to write these ionic formulas, but I should be able to explain what it means. What does it mean that there's a 2 by the iodine? Well, there's 2 atoms of iodine. It makes it neutral. Magnesium gives away 2 electrons. Each iodine atom will gain 1. We should be able to explain the electron transfer in these compounds. Naming compounds, binary compounds, meaning that there's just 2 ions, should be a piece of cake. There's a positive ion and a negative ion. The positive will always come first, the positive cation. And we'll write the full name. It doesn't matter if it's capital C, lowercase c. Calcium. The second ion will end in IDE. Chloride. Done. You do not need to say calcium dichloride. In fact, don't say calcium dichloride. If you just say calcium chloride, I can tell you that there are 2 atoms of chlorine because I can look at the charges on the periodic table. Calcium's charge is +2. Chlorine is -1. Oh yeah, to make this neutral, I'm going to need 2 atoms of chlorine. I can write the formula CaCl2 from just the name calcium chloride. You don't have to say dichloride. The second one, piece of cake, aluminum. Oh boy, ketchup. aluminum oxide. I don't have to say dialuminum trioxide. Now, there are compounds that do have all that monodi-tri. That's covalence. That's nonmetals. We'll talk about those in a little bit. Not now. If it's ionic, it's going to start with a metal. And I don't need monodi-tri any of that stuff. This is just lithium phosphide. They should all end in IDE. Lithium is always +3 or +1. Phosphorus is always -3. 1 minus 3. To make this neutral, I'm going to need 3 atoms of lithium. I can tell you the formula is Li3P. You don't have to say trilithium phosphide or anything like that. Now, these examples all had cations that fill in groups of the periodic table that only had 1 charge. What if we visit our friends, the transition metals, for a second? The transition metals can have more than 1 charge, which makes them sometimes kind of stinkers. The charge used in a particular compound will be noted with a Roman numeral. And now a misconception. That Roman numeral indicates the charge. So I don't really have to look at a periodic table to get the charge on manganese. And in fact, it wouldn't do me any good because manganese is a transition metal. It doesn't follow trends. Manganese can have like 5 different charges. This is Roman numeral 6. Manganese is +6. The first element is always the positive cation. So the Roman numeral will always be a positive charge. Sulfur is always -2. So the manganese is interested in losing 6 electrons, but the sulfur only can take 2. So to make this neutral, we do some very complicated math. And we might just do that in our head. MnS3. There we go. Manganese 6 sulfide. Some of these transition metals can have some kind of crazy charges too. You might find 4, 5, 6. You could even find a charge of 7. You kind of have to remember that we're dealing with d orbitals, those high energy unstable d orbitals. Don't follow a lot of trends and patterns. So don't freak out if you find something with a charge that seems a little bit goofy. A +6 is totally acceptable on a transition metal. Okay, so here's the misconception. People will look at that Roman numeral and they read this. I mean, it's read as manganese 6 sulfide. So can you see where I'm going with this? They'll write the formula as manganese 6 sulfide. They'll think that the Roman numeral is somehow like the subscript. Manganese 6 sulfide. Well, there must be 6 manganese. No way. Bad. Sad face. The Roman numeral is the charge, and then I still need to balance that with the charge of the anion. So again, I mean, for the most part, writing formulas with transition metals is not a big deal. It's no new rules. And in fact, sometimes it's kind of easier. You don't have to look up lead on a periodic table. The Roman numeral is telling you the charge. This is Roman numeral 4. Which, by the way, those two are ones that people mix up a lot. When the V is first, V1, that means like add 1. Say it's 5 and 1 for 6. If the V is in the back, 1V, that means subtract 1 for 4. So this is lead 4 oxide. Oh, piece of cake. To make this neutral, I need 2 oxygen. Lead oxide. I need 2 of them. It's not as it's read. Lead 4 oxide. No, sad face. No, the 4 is the charge on the lead ion, and then I balance it with the oxygen. Now this leads us to different formulas of the same 2 elements. This is lead 2 oxide. Lead plus 2 oxide. Ooh, that's neutral right away. So my formula is really just PbO. And now you may recall something called the law of multiple proportions, which says that you can have elements join in different ratios, but be aware that they'll have different properties. And we'll find that with a lot of these compounds, if the transition metal has a different charge, you could have the same elements, but you'll end up with different ratios, different formulas. And those different compounds will have different properties in the lab. Naming compounds with transition metals can sometimes cause more problems. Usually the formula writing is okay. The transition metals charge is noted by the Roman numeral. But if you have to write the name, then you need to figure out the charge on that transition metal. And I guess first of all, the battle is recognizing that you have a transition metal. So if I see iron sulfide or cobalt phosphide or any transition metal, iron, silver, any of those guys in the center of the periodic table, my mind is immediately thinking that I'm going to need a Roman numeral when I complete my name. Now, I often start these with just the names of the two ions. The cation, the positive, gets its full name, iron. And the anion switches to IDE. And I would have the same thing here, iron, sulfide. But if I notice that the first element is in the transition group, I will need a Roman numeral. There are two different forms of iron sulfide. If somebody tells me go in the lab and grab some iron sulfide, I would say what bottle? And they're going to have compounds with very different properties. So we need to be specific when dealing with these metals that can have multiple charges. I need to kind of work backwards here. There are no negative anions that have multiple charges. So if you look up sulfur, its only choice is -2. So from here I can go backwards and figure out the charge on the positive, knowing that the ion or that molecule needs to be overall neutral. So if there's only one sulfur and one iron, this iron must have been a +2. +2 -2, neutral. This is iron 2 sulfide. And the second one, I have 3 atoms of sulfur. 3 atoms of sulfur. They each have a charge of -2, leaving me with a -6. I need to get a +6 out of my iron. Now there are 2 atoms of iron, so if each atom of iron had a charge of +3, +3 times 2 would give me a +6. So the Roman numeral that I put in this box is the 3, or these parentheses. Each iron is +3. Now this chart here gives you some common metals with multiple charges. I wouldn't try to memorize this whatsoever. It's not necessary. If I recognize that it's a transition metal, I need a Roman numeral. So I'm automatically going to look at the charge on the negative and balance that with the charge on the positive. The only thing that we should mention about this table are these guys. Tin and lead. Tin and lead are not transition metals. They're at the bottom of the carbon family. However, they do commonly have more than one charge. They're both usually either +2 or +4. Tin and lead will always have a Roman numeral. So that might be one to watch out for. It's technically not a transition metal, but with tin and lead, you definitely need that Roman numeral. And you'll always see it in a written name. So don't freak out if you see that lead +2 and you're thinking, but lead is in the carbon family and it's supposed to be ±4. Tin and lead don't follow that perfectly. There's got to be exceptions. Otherwise, this would be way too easy. Other ones that we should note specifically are these two. Silver and zinc. silver is 99% of the time +1. And zinc, 99% of the time is +2. If you don't see a Roman numeral with a silver or a zinc compound, you can assume that the silver is +1 and the zinc is +2. On the flip side, if you leave the Roman numeral out for zinc and silver, I will assume that you mean silver +1 and zinc +2. They've got cadmium listed too, but cadmium is really not quite as common. The silver and the zinc are probably the ones that you're going to run into most often. If you don't see a Roman numeral, you can assume that it's those listed. And this last one they have here, cobalt. So again, I don't try to memorize these charges on the chart. These are maybe just most common charges. But a lot of these transition metals can have multiple charges, more than 2 even. This is definitely going to need a Roman numeral because cobalt is a transition metal. So this will be cobalt something phosphide. To figure out the charge, I'm working backwards. Phosphorus is always in the group that's -3. There are 2 atoms of phosphorus, giving me a charge of -6. There's only 1 cobalt, so it feels kind of weird, but I'm going to say cobalt 6. And then you'll say, but cobalt 6 is not listed on this chart. Well, it might not be the most common form of cobalt, but it does exist. With a lot of these transition metals, it's cool. As the charge changes, the color of the compound changes too. Cobalt compounds can come in a rainbow of colors, which kind of signifies the different charges. Cobalt can have like 5 or 6 different charges. Yeah, 6 isn't the most common, but it does exist. So be on the lookout for those transition metals or tin and lead. When you're writing their names, they will need that Roman numeral so that somebody can go in the lab and find what you're looking for. If you just say iron sulfide, I can't help you out because there's going to be more than 1 bottle of iron sulfide. So work backwards. Find the negative charge and then balance that with the positive charge.